Okay, hello and welcome to part 2 of our look at Key Stage 4 study into waves. So our last lesson we actually just had a look at the two main types of what actually waves were. So we had our transverse and our longitudinal waves. If you're not quite sure what those two things mean, I would recommend you go back and have a quick look at that. What we're going to do today is have a look at what is meant by the terms amplitude, wavelength, frequency and speed, and we're going to do a little bit of maths as well. We're going to have a look at working out a wavelength when we know our frequency and we know the speed. So yeah, let's get started. So first things first, amplitude and wavelength. So as we've got here, as we were talking about in our first lesson, we have a transverse wave here. So what it's actually done, as a transverse wave or as a vibration is formed into a wave, what it's called is called a pattern of disturbance. So this actual wave shape, this transverse wave shape, is what we call a pattern of disturbance. Now the amplitude, all the amplitude is a measure of the maximum disturbance from the point of no disturbance. Okay? BBC Bite Size is really, really good for explaining this. This is where I got the majority of the pictures from this one lesson today. So as I said, the amplitude is it's the maximum disturbance from the point of no disturbance. So it's not from the bottom to the top, it's from the centre line where there is technically no disturbance to the point that it actually reaches the top part of the maximum disturbance that it's going to get to. So this is the amplitude. So it's not the whole height, it's from the 0 point up to the top. So our wavelength is actually going for a complete length of wave. So it's as long as you measure it from the same point of one wave to the same point of the next wave, then it's fine. You can take it from any point. So if I wanted to measure it from, say I wanted to measure it from here to here, that's fine, that's still a wavelength. Although I've got it measured out to go from here to here, that's fine. As long as you're measuring it from one point on one wave to exactly the same point on the other wave, it doesn't matter, it will still give you the same point. I mean, you know, if you worked it out, you know, you could do it from anywhere on there really. As I said, we've got it marked out that it would be from here to here. But as long as you take it from one point and measure it to exactly the same point on the following wave, then it really doesn't matter because you will still get the same result of exactly how long that wavelength is. So remember, amplitude is the measure of maximum disturbance from the point of no disturbance. So it's from the centre point to the highest peak. Or alternatively, you can have negative amplitude as well, from the 0 point to the lowest trough. Whereas wavelength is from one point of the wave to the following point of the exact same place of the next wave, and that is your complete wavelength. So what happens if amplitude, or if you change amplitude or you change wavelength? So this is where you come into something called frequency. Now frequency can be explained in two ways, which they sound a little bit different, but exactly they effectively mean exactly the same thing. It's either the number of complete waves per second, or it's the number of complete waves that pass a particular point per second. They mean exactly the same thing. The only thing you have to really remember is it's just the number of complete waves that pass in a second. It's waves per second. Effectively, it's, you know, speed is meters per second, frequency is waves per second. Now the unit of frequency is something called hertz. Not like it hurts, but actually hertz. H-E-R-T-Z. God, I have to think about that, and that's really bad. But most of the things that we have in modern day life have really quite high frequencies. So you would have something generally written down for any power supply or any supply or any electrical goods that you use would be either kilohertz, megahertz, gigahertz. Obviously kilo is 1,000, mega is 1,000,000, and giga is 1,000,000 or 100 million. So if the frequency increases, as you can see here are two different types of frequency here. Our top one has got a higher frequency than our bottom one because there is more complete waves passing in one section than there is in the bottom section. So as frequency increases, our wavelength decreases, but the amplitude doesn't necessarily change. So you can still have the same, as you see, these waves are still the same height. They're still 4 blocks high. So the amplitude is still the same. So our amplitude here would technically be 2, if we're going to talk in square units. So our amplitude here is 2, but our wavelength is considerably shorter in the first one, in this top one, because the frequency is higher. So therefore the amplitude has stayed the same, but if frequency increases, then wavelength decreases. Okay? So what we're going to do now is we're going to have a look. The different uses of saying the different types of frequency. So human hearing, that is basically a range of 20 to 20,000 hertz or 20 kilohertz. I'll tell you a really good thing actually, if you want to be a little bit cheeky and still trying to be able to use your mobile in school, which obviously I'm not condoning, but should you feel like you can, this 20,000 hertz, up to the age of probably your early mid-teens, as long as you've not been listening to too much loud music, you should still be able to hear between about 18,000 or 18 kilohertz and 20 kilohertz. I'm in my late 20s now. I can hear 15 kilohertz, I can hear 16 kilohertz, but I can't hear 17 or 18. And I guarantee that most of your teachers, who will probably be older than me, will definitely not be able to hear 18 kilohertz. You might even get away with 15 kilohertz. So you can get apps on your phone, and when you get a message, it actually gives a frequency of 15 kilohertz or above. So they won't be able to hear it, you'll still be able to hear it, but obviously you didn't get that from me. So FM radio, for those of you who still listen to FM radio, the frequency for here is 88 to 100 megahertz. So we've jumped up now from 2020, so we're now on sort of 88 million hertz. So that's sort of where FM radio sits. Your iPhone, whatever mobile phone you have, there's quite a big range here from 870 to 1800 megahertz. So the frequencies are getting quite high now. There's a big range there just because of obviously the different types of technology we have in phones now. They all want to do different things and they all have different purposes. So this higher range would be used for probably more of your smartphones, like your iPhones, your Samsung Galaxies, things like that. And then your microwave, the wave frequency here is 2.5 gigahertz, so that's 2.45 billion hertz, or billion waves per second. And obviously we all know you don't really want to be sat in a microwave when it's turned on. We all know what happens with that. Microwaves can heat you up on the inside, and they're pretty dangerous things. The interesting thing though is that if you take 0.05 off of this 2.45 gigahertz, go to 2.4 gigahertz, a lot of wireless internet in workplaces, even in your home, is roughly around this 2.4 gigahertz frequency. So there's a subtle difference, although obviously we're talking about 2.0 plus, we're still talking about 5 million hertz in terms of wave frequency. But yeah, that's the difference between a microwave and your wireless internet. Another useless fact for the day. So how fast do waves travel? So sound waves, so here we are, we've got our wave equation, okay? So speed is equal to frequency times by the wavelength. So hopefully by now you'll all recognise this, this diagram for your formula triangle. So we've got speed at the top, frequency bottom left, wavelength on your right. So yep, speed, which is always meters per second, frequency as we discussed, which is in hertz, and wavelength, which is actually measured in meters. Again, it's a measure of distance, so it's a standard unit for it to be meters. So yeah, so speed is equal to frequency times by wavelength. So let's have a look at something. So this here is, I don't actually know which plane this is. If there's a tornado, I'm sure I'll probably get slated by anyone on YouTube that does actually bother to watch this. But this is our plane, which is actually breaking the sound barrier. So we know that sound travels at 340 meters per second. Just think about that for a second, 340 meters per second. That's pretty fast. But now think that the speed of light is roughly, and I do say roughly, 300 million meters per second. So relatively speed is really slow. It'd be like me trying to run 100 meters against Usain Bolt. You know, it'd just be ridiculous. It's just not a contest. You know, the speed of sound is at 340 meters per second. So, because I'm a massive geek, and I'm a bit of a gleek, as you can probably see from these two, and I recently went to London. I went to go and see Wicked, and to sound really, really cheesy, it was wicked. It was awesome. So I'm hoping that some of you have seen Glee and seen the episode where these two, Kurt and Rachel, try to sing the signature song from Wicked, which is Defying Gravity. Now, at this point, the last note in that song is a high C, which is also called a C6. Now, the average vocal range for taking men and women together, the vocal range is generally speaking between 80 Hertz and 1100 Hertz. So as you can see here, we've got the frequency here for the high C, which is 1046.5 Hertz. So it's right at that top average range for your vocal voice. But as we were saying before, we had our triangle up earlier, our formula triangle up earlier. So we know the speed of sound, and we know the frequency of high C. So what we can actually work out is the wavelength of that actual note. So if we write up our triangle, so we had speed, which on top of frequency and wavelength. So we know our speed and we know our frequency. What we want to work out is this wavelength. So obviously we need to readjust our equation to make sure we get it the right way round. So we want to work out wavelength, so therefore what it's actually going to be is the speed divided by the frequency. So the way that this works out then is that our wavelength is equal to the speed of sound, which is 340 meters per second, okay, and that is divided by the frequency of our note, or our C6, which is 1046.5 Hertz. So obviously I'm a geek, I've already worked this out, so I'm not going to go off into a calculator and that. But what that actually works out is that you get an answer of 0.32, and that is actually in meters. So the wavelength of this C6 is actually 32 centimeters. So if you're thinking at the point that Kurt did it in practice, but in the actual Glee, I am this much of a Gleek, I'm sorry. In the actual point when he's singing it, he couldn't hit it. But Rachel did hit it, and when I went to go see Wicked, the young lady that was singing and was being Alfalfa absolutely nailed it. At that point, the sound wave that is exiting her voice is 32 centimeters long, so it's just over the length of a ruler. I know that's massively geeky. For those of you that didn't appreciate it, I'm sorry. For those of you that do appreciate it, go on the Gleek, go on the Wicked. So our overview there, we've had a really geeky look at amplitude, wavelength, frequency and speed. So yeah, we've looked at the differences between those and our equation for speed and how to work speed out as well as if you had the others, you could obviously backtrack and work out frequency, and as we did, we worked out wavelength. So that's the end of today's little lesson. Next lesson, we're going to be looking a little bit more in depth into actual sound and ultrasound as well. Thanks very much. I'm Ian McDowell. I'm a student at Brighton University. Cheers.